Thanks everyone for showing up for your learning today. Today we're going to be taking a look at exponential growth. But I want to start with a quick poll, a quick show of hands. Raise your hand if you would like to have more money in this lifetime. All right, cool. So this unit is actually very important for you because as you know, time is money, and the way in which time and money are related is exponential in nature. So we want to have a good grasp of these concepts so that you can make use of a very plentiful resource for you and limited resource for me, which is time. You don't need to be like me and squander the years between 16 and 42 traveling around the world and finding yourself. You can go ahead and put together some money. So here we go. Let's take a look at this idea that I want to show you. If I have something like x squared, we know this shape, this typical shape, right, of the parabola. But what if I had something like 0.001 to the x? Notice that looks very boring. Looks like a flat line. Like the a value is so small. But what if I zoom out, everyone? If I zoom out, you'll see that the distinctive parabola shape returns. It's always there. I just need to zoom out to quite a high level. Okay, now let's zoom back in, and we'll zoom in on the vertex, and I'll show you something that's also very boring. Okay, let's say I give you 1% interest on $1,000. That would create an equation that would look like this. 1% interest on $1,000.
It's 100. It's 1% on top of the 100.
Yeah.
And that's an
So here, if I give you 1% interest on $1,000, when we go forward 10 years, you've added around $100, right? Shouldn't surprise us. A little bit more than $100 to our initial 1,000. So it's not very exciting. I made $100 over the course of like 10 years. Not very exciting. But if I zoom out, you'll see what happens here. See the shape. Look at the shape of money. This is the shape of money in our world. Exponential equations, doesn't matter how much I flatten them like this. If I flatten that and I say, I'm not giving you 1% on your money, that's actually 1,000th of a percent. If I still zoom out, I will still get that trademark exponential blows up shape.
like 50,000 years.
Yeah, okay, but that's also not a reasonable interest rate. That interest rate is effectively zero over the human lifetime. What I want to show you is they always have this shape. They always blow up at some point and get very, very steep. It does not matter how big or how close to 1 I make that number. If this is the other way, if I have something like 0.99999, you'll see it goes the other way. And that's what we were just seeing with numbers less than 1 getting smaller as we go through the y-axis. Numbers greater than 1 getting bigger as we go through the y-axis. Today we're looking at the happy side of that, exponential growth. So let's take a look. Exponential growth. So the function might look like it's increasing slowly at the beginning, but then at some point it's going to start growing rapidly. And this is the way exponential growth works. One thing we learned as a society during COVID is that the human mind does not understand exponentials intuitively. When you hear something like, oh, COVID cases are growing by 5% a day, it does not sound scary. Actually, 5% a day is an explosive rate of growth because it grows as a factor of the number of cases. As the number of cases grow, so does the rate of growth. And that's what causes it to blow up as the number gets bigger. Okay? So let's take a look. Let's keep going. And okay, let's keep going. Let's do the math and not the public service announcement. All right. So this is what our equations for exponential growth are going to look like. We're going to have the function, which is telling us the amount. This big A is like amount. Oop, I need a pen. Big A is like amount at time t. When time equals t, we get the amount A. That's the output of these functions. That's amount. Does amount have 2 m's or 1 m? I think it's 1 m, right? Amount. Yeah. Okay. then, so how do we create them? Well, we have an equal sign. It's a very important part of our function. Is equal to the initial value here. It looks like a coefficient. It's something that's going to be multiplying in here. That is an A transformation, and it's also the amount at time 0. Let's take a look at why this function will have an amount at time 0 of A. If I have A at 0, then what that will be is it will be equal to A, which is that number there that we're talking about, multiplied by B. B is called the growth factor. We'll talk about that in a second, raised to the power 0. Hey, Isaac, what's B to the 0? 1. Doesn't, well, you don't know what B is. How can you so confidently tell me that B to the 0 is 1? Because everything to the 0 is 1. Very good. So this is equal to A times 1, which is just A. So that's why A is the initial amount. You see it there? It's a little bit like reading a y equals mx plus b and knowing that b is the initial amount. Because when x is 0, m times x is 0, so you're just left with b. In this case, b to the 0 is always 1, so you're always multiplying a by 1, so a is your initial value. Now b is the growth factor. And we're going to build the growth factor with this little equation 1 plus r. All right? Now let's create an example where r is the growth in the growth percent as a decimal. All right, and we'll see why this is true. I gave you an example of we have $1,000. Okay, this is going to be the amount of money that we're going to have at time t is going to equal $1,000 multiplied by 100% of the money plus the growth, maybe 1%, raised to the power time. Okay, and that would be this equation that we looked at over here. I'm just going to type out a new, I'm going to get a fresh Desmos and look at that. Leave. Here we go. We're going to look at $10 here, and it's going to grow at 1.01. That will be raised to the power x, and then here is our money. There it is growing. After 2 years, you see we've got $10.2. After 6 years, we've got $10.6, and it's growing. But the amount of money that it's growing is growing. See how its rate grows? So that over a non-human amount of time, we actually can end up with a significant amount of money. Yeah. So the reason why we create our B values this way is because if I tell you you're getting 1% interest added onto your money, next year you will have 101%. 100% plus the growth. The year after that, you will multiply the money you had in the second year by the growth factor again. So you are raising to an exponent is the most efficient way to express that. After 5 years, you will have multiplied by your growth factor 5 times. You'll have 1.1 raised to the power 5. 1.01, sorry, in this case. 1.1 would be 10% growth. So let's keep going. Let's keep looking at some more examples.
10%.
So let's break down these two different exponential growth equations. In both, the initial value is easy to see. The initial value here is 400. The initial value here is 243. I don't know why I wrote down 6. That's very strange. 243. So those are our initial values. Our growth factor is just this number. We call this number the base of the exponent, the growth factor. So that's 1.12. And this one is 1.6. But if I asked you, by what percent each year is that growing?
112. Well, 12%.
Well, it's growing by 12.
Yeah.
So you were going to say
12%.
12% increase, right? Yeah. It's 12% more than 100. So this is 12% growth. This one, good, is 60%. Why would you say 60 and not 6%, Camden? Yeah. So this is the, did I change that number when I added that 0?
No.
No. But feel free to add this 0 if it helps you avoid mistakes. And remember that the percentage is the next 2 decimal places. Percent means per 100. Cent means like century or centurion or centennial. Has to do with the number 100. Percent means per 100, so you need to go to the hundredths place.
So you just ignore the one.
So there you go. That. Okay. Now let's take a look at solving some examples. Okay, we have our population of 100 frogs, and we want to know how many frogs there'll be in 5 years. Let's take a look. I would make a little chart. My A, which is my initial amount. There's 100 frogs initially. My B is my growth factor, and I'm going to build that with 1 plus R as a decimal. R is equal to 22%. What's 22% as a decimal? 0.22. Excellent. So my B now is equal to 1.22, and that gives me my equation. Okay. So I can look at this and I can say, well, the population of frogs is a function of time. I called this A of t up there, but I prefer P of t for this. Population of frogs as big P. Okay. Doesn't matter. They're letters. You can use the letters you like. Sometimes I name functions g of x because my name is Grant and I feel personal about a function that's g of x. Okay, so P of t is going to be equal to a multiplied by b raised to the power t. So just input. P at t is going to be equal to 100 multiplied by 1.22 raised to the power t. And now I've been asked to find what's the population in the 5th year. So input that for t. That'll be 100 multiplied by 1.22 raised to the power 5. And if you can do that in your head, I was watching a video the other day where the presenter was like, and if you can do this kind of question, I don't know why you're watching my video. Like, go do more maths, you person who will change the world with maths. I don't know how to do that in my head, so I use a calculator. 1.22 raised to the power 5 equals 2.7. 2.70.27. So what we're finding is that after applying that growth 5 times, like I multiplied by that growth, every year the number of frogs grows based on the number of frogs that are there. And it grows by 22% each year. It does not grow as a line, it grows as one of these exponential curves. And it will have grown by a factor 2.7 after 5 years. So we can put that into our equation. We could say P at 5 is equal to 100 multiplied by 2.703 or so with rounding. Yeah, 2.703. Okay, that's rounded. Now I multiply by 100 to find the value. This is equal to 270.3. Anyone else uncomfortable imagining 0.3 frogs?
I don't think I got that.
Some of us are a little uncomfortable with that idea. Okay, good. So in that case, round your answers to the nearest reasonable number. We expect to have 270 frogs by rounding. So we would say, therefore, there will be 270 frogs after 5 years. And let's have some fun in Desmos and find out when the first 2 frogs started having more frogs. Let's find out how many years ago there were only 2 frogs when this whole frogs growing by 22% a year thing got started. So we put it into Desmos. Go ahead and graph your equation. 100 frogs multiplied by 1.22 raised to the power x. We're way too zoomed in to see. So what I'm going to do is change the scale. And I want to see x values that go negative is fine. Let's say negative 50 or so. And then bigger x values, we already saw up to 5. That's fine. Y values were good. So let's go. So this was our solution. We saw that after 5 years that there would be about 270 of them there. You see? That's 5 years. 270.27. So we had trouble imagining 0.3 frogs. We didn't like that idea, so we stopped. We rounded. Desmos didn't. And then here we could go back. We could graph the line y equals 2 to find when were there 2 frogs. It was about 20 years ago. There were only 2 frogs, and they started growing. So you can use these exponential equations to predict the future, but also examine the past. Cool, eh? And that's with negative values of x. Great, let's keep going. In this question, we have to solve for t. All right, so the population of a city grows at a rate of 5% per year. Write down your numbers as you find them. My r is equal to 5%, which is equal to 0.05. Maybe you circle these things per year, so we're measuring by year. In 2003, I'm not really sure what to do with the date right now, so I'm just going to leave that. I know what to do with it, but I don't want you to be confused. Was 400,000. So that's my A initial amount. Was 400,000. No, that's the amount that we had in 2003, and we want to know in what year will the population reach 1 million. So I might set t as equal to number of years after 2003. Does that make sense?
Yeah.
So t at 0 is 2003. T at 1 will be 2004. Okay? And then I know that my population at some value time of this city, because it's growing, and I know that these shapes will grow, y is going to be bigger and it's only going to get bigger, is going to be reaching 1 million. So I want to find when that happens. So I make my equation. Oh, first I need my b, my growth factor. My b is equal to 1 plus r. In this case, it's 1.05 because I'm going to add this r value to 1. And that will give me 105% of the people next year that I have this year. And every year, those people multiply themselves by 1.05. That's why we use repeated multiplications here to grow this, and why it creates a curve instead of a straight line. A straight line will be adding the same amount each year, but we're not doing that. We're multiplying by 1.05 every year. So here is our function. Our function looks like this. P of t is equal to 400k multiplied by 1.05 raised to the power t, where t is the number of years after 2003. Now, let's input for p of t on that side of the equation, and we're going to do all the algebra we have to isolate our variable. Oh, but our variable is an exponent. I really only know how to solve that if I can make the bases the same. Remember we learned how to make the bases the same before to solve for exponents?
Yeah.
Let's see if we can do that here.
But that's 1,400,000.
Yeah, we can't really do that, so let's take a look. So P of t is equal to 1 million. 1 million, put it in, is equal to 400,000 that grows for some number of years at this percentage growth. Now get out your inverse operations pen and do all the inverse operations you can. We can divide this 400,000 away. And then we find that 5 over 2, or 2.5, is equal to 1.05 to the t.
Wait, how did you know that?
Well, I reduced 1 million over
Oh, it's
400,000.
10
You
over
can't do 1 million over 400,000 in your head?
It's 10 over
It's 10 over 4. It's 5 over 2. Yeah, it's very easy. I was joking with you because most people don't do that in their heads. But if you maybe get a little bit sauced by your math teacher who's a little saucy and says, you don't do that in your head, and raises an eyebrow at you, you're like, oh, I'll look for the shortcuts next time. Yeah, just a little saucy. So now I'm actually stuck. I don't really know how to do 1.05 and express that as a power of that. It's a little too ugly. 21 over 20? Youch. It's not really a power of 5 over 2. So we have now guess and check.
What?
Yep. Guess and check. Or do you want to solve this algebraically?
Oh, yeah.
Good. Okay, I recommend you do very well in this course and then go take grade 12. Because in grade 12, you'll learn to solve this algebraically, but it's not part of our curriculum.
So we just guess and check.
Yeah, we're going to guess and check. And I'm smiling under my mask. You want to know why?
Why?
Because everyone needs more practice with guess and check. It's a really good thing to build your number sense, to build your ability to solve these types of problems, and it's always available to you. Oh, I don't know how to do this algebraically. Let's get close enough with guess and check. And if you get really good at guess and check, you can solve a lot of problems. So let me pause this video and then mistakes. This is what I suggest for your guess and check solutions is you simplify it as much as possible with algebra, and then you're going to go like this. You're going to say different values of t and we want to do 1.05 to the t, and our target is 2.5. That's our target, or 5 over 2, same thing, but your calculator is going to give you a decimal. Where do you want to start guessing? 1? Okay. Okay, that's funny. But if you did 1, then you would get 1.05, and you would say that's too small. It's not nearly close to 2.5. 19, let's try 19. So then we do this. You go 1.05 raised to the 19. Don't dare do that longhand. It's way too hard. 2.52. Oh, you already did it, didn't you? 2.52. That's very good. 2.53. Oh, because we found it here when we did inverse operations on that this growth has to be about 2.5, right? How long does it take the population to double and then grow by half? So what would we have to guess? So we just guess and check, yeah. So you guess to 19. Okay, so this is how guess and check works. Is let's say you try 10, and then you do 1.05 raised to the power 10, and then you get, oh, we got 1.6. We're part of the way there, but we're not really there yet. So when we try something bigger, maybe 20. Maybe you try 20 next. 1.05, and you raise that to the power 20, and you get, oh, 2.6. Cool, we're very close. You try a little less. And then actually, it works out that it's between the year 18 and 19 that it goes over 2.5. Now we take a very careful look at here is 18. 1.05 raised to the power 18 gives us 2.4. Okay, that's 2.4. So you can see somewhere between the 18th year and the 19th year, maybe around late September, it's going to cross 1 million. So it's within that 18th year. Now we look carefully at the question, in what year can we predict the population to reach 1,000? So if Caden bullseyed it and said 19 is the closest integer, and then added 19 to 2003, he would get 2022, and he'd be incorrect. Because at the beginning of 2022, the growth has already exceeded that amount. We were asked, when does the population cross 1 million? So let's take a look in Desmos at this. And people notice, like, how often do I say, let's look in Desmos? You want to do this too with your homework. Look at it in Desmos, see the population trends, and analyze. When you look at these things in Desmos, you'll learn a lot. 400,000, that's 400,000 there, multiplied by 1.05, raised to the power x. Okay, I can't see anything. Well, I need to look at y values that go up to at least 1 million. Let's look at, there we go. And then I don't really care about backwards time. I really only care about forwards time. Okay, so this is a pretty clear example of what's happening. And then I can graph the line y equals 1 million. There it is. And here's my intersection. 18.78. So guess and check gave us between 18 and 19, maybe towards the end of the 18th year. And so that's it there. And so that's how graphically you would find the solution. We could also graphically find fun things like when were the two people who moved to this place and said, let's start a family, and they started growing exponentially. But that assumes everyone is related to those two people. Okay, maybe don't do that. It's not how populations work. But anyway, you could do that, and you could go back in time here. Now, one more idea about this question before I release you to do a little practice before you go home is we can also change this so that instead of having x being the number of years after 2003, I could change this and say, no, I actually want to do x minus up here bracket, and I'm going to go in here, x minus 2003. And I'm not going to show you this. Here is the population in year 0. It was effectively 0. If I zoom in enough, you'll see it's not 0. But then, if I go over here and I show you things like, well, in the x-axis, I want to show you between the years 1900 and the years 2050, here's our population. Here's what the population was in 1900 for this city. It was only about 2,070. And then this was the population in 2003. Well, it was our initial value of 400,000. There, you see? Where is it? Oh, 2003, 400,000. There it is, 2003. And then it starts growing, and we see that it passes a million there in 2021.7 or so, 2021.8. All I did was I added a D transformation. See the D transformation I did there? I subtracted 2023 from my exponent. That moved the whole equation, the whole function that way to the right, 2023 units. So now my x values match with my years. So it's a little bit more elegant to show this if you were doing a research paper on the population or something. I say this is the population in what year? Okay. And I could use this to make predictions about the past as well as about the future. When will this population blow up and go way off the page? Now, notice how fast this population is growing at only 5% growth. And think that during the pandemic, Collingwood was growing at about 13%. 13% doesn't sound like much. This is 5%. 13% is explosive growth. It's not sustainable. It cannot continue.
What happened? Oh, the price of houses went huge.
Price of houses went up, and also the Collingwood banned new developments. They said no more new developments for a number of years. We needed to rest on that. We're not hooking you up to water if you build a new thing. So that effectively stopped new development because it was too fast. A small community like this can't keep up with, no community can keep up with that and not have stress. So the practice is also inside your stuff here. It's the exponential growth questions. Try.
Bro, Dan, you just sent me a firewall.